Okay, so we are going to start with question number 3 today. Part A. Aqueous acidified iodate 5 ions, IO3. Iodate 5 ion means iodine have a +5 oxidation number over here. Reacts with iodide ions as shown. Okay. The initial rate of this reaction is investigated. Table 3.1 shows the results obtained. Okay. The rate equation 1 minute. 1 minute. Right? Okay. The rate equation for this reaction is rate is equals to rate constant K, concentration of iodate times concentration of hydrogen square times concentration of iodide square. So see, if the rate equation, then we know that order with respect to iodide is 2, order with hydrogen is 2, order with respect to iodate is 1. Explain what is meant by the order of a reaction. So we know it is the power by which the concentration is raised in rate equation. Walaikum assalam. Okay, so now what they are saying, complete table 3.1, the order of reaction with iodate, as there is no power, so it means its order is 1. The order of reaction with respect to hydrogen ion concentration as its power is 2, so its order is 2, right? The order of a reaction with respect to iodide as its power is 2 in the rate equation over here, so its order is going to be 2, and the overall order we just add them, so it is going to be 5. Is this clear to all of you? Okay. Use your answers to A2. Okay. Sketch the lines in figure 3.1 to show the relationship between the initial rates and the concentration of iodate and iodide. Okay, iodate's order is 1. So if the order is 1, so there is a linear line like this from the origin, right? Because both the rate and the concentration changes with the same factor. And over here, when the order is 2, so it would be like this. Okay. Now, part 4. Use the data from table 3.1 to calculate the rate constant K from this table for this reaction. Include the unit of K. Okay. So, here is table 3.1. We know the concentrations. We know the initial rate. And we know the rate expression as well. So, we have to put all the values and make the K subject. So, if I'll make the K subject, then the equation would be K is equals to rate, concentration of iodate times concentration of hydrogen square times concentration of iodide square, right? So the rate is 4.20 exponent minus 2. And the concentrations are 0.04, 0.04, 0.015 square and 0.025 square, right? Let me see. Yeah, 0.015 and 0.025. Can anyone calculate and tell me the answer, please? Because in second order, the rate gets doubled as the concentration is increased. By which factor the concentration is increased, the rate increases by square of that factor. So if you go through the notes, you will find the same shape of the graph that we have discussed. Okay, Abdullah? No, in second we don't have a hydrogen ion concentration. That's why I didn't take it. Shahan, you are getting Shrey 7.47, Shahan 7.46. So who rounded off it correctly? 7.47. 7.47. Exponent 6. Okay. Now we have to figure out its unit. So in the numerator, we have a rate which means mole per dm³ per second. In the denominator, we have mole per dm³, which is going to be cancelled out. And then we have a 2 squares of mole per dm³, right? Mole per dm³ whole square and mole per dm³ whole square. So it is going to be mole inverse 4 dm12 second inverse. No, 1 minute. It's a minute. No, don't. So we don't use second, we use minute. So it's a minute inverse. Is this clear? Okay, now use the data from table 3.1. Calculate the concentration of hydrogen ions in experiment 2. So see how you will calculate it. Okay, so it's a little tricky. There are two ways to calculate this. One is that now you know the rate constant. You will put the everything in the rate expression and make the hydrogen ions concentration X. The other one is that, see, if we look at this, this is increased by the factor of 3. So as its order is 1, right? So this must also be increased by the factor of 3. But, okay, by which factor it is increased? 1 minute. It is actually decreased by half, right? It is decreased by 2. So it means due to this, it is going to be decreased by 4 because it's a second order with respect to this one, right? So multiply by 1.3, multiply by 3 times multiply by 1/4 because it's decreasing by half. So the rate is going to be increased by the factor of 4 as it's a square. The rate is second order. Okay, now. And the factor by which it's affected by hydrogen ions concentration, that is X, we don't know, right? Because we don't know its concentration. So from this, can you calculate the factor by which it's changed due to the hydrogen ion concentration? So it is going to be 4. Oh, okay, sorry. X is equals to 7.09 exponent minus 2 multiplied by 4 divided by 3 into 4.20 exponent minus 2. Is this understandable? Are we getting 2.25? Okay. So just take the square root of it because it's second order with respect to hydrogen ions, right? 1.5. So multiply 0.01 by 1.5. So if you multiply it with 1.5, you will get the concentration. That is the one way. Or the other way is you just use the rate expression because you have calculated the rate constant K initially. So you know the K, you know all of the values, you put make the hydrogen ions subject and then calculate it. So what is the answer? 0.015 multiplied by 1.5. 0.0225. So 0 0.015 multiply by 0. No, multiply by 1.5, right? So we get 0.0225. So either you will do this way, or instead of this, you can use the same rate equation because you got the rate constant K. So is equals to concentration of iodate times concentration of hydrogen ions square times concentration of iodide ions square, and keeping it, making it a subject, you can calculate it. Okay. Now, 6. This reaction is repeated in two separate experiments. Okay. The experiments are carried out at the same temperature with the same concentration of iodide and iodate. Okay. One experiment takes place at pH 1 and the other experiment takes place at pH 2. Calculate the value of rate at pH 1 divided by rate at pH 2. Okay, so it's very easy. What you are going to do, if the pH is 2, then what would be the concentration of hydrogen ions? The concentration of hydrogen ion is equals to pH. No. No, what was the formula? Exponent minus pH. So, if the pH is 1, then raised to the power, it's 0.1 and 10 raised to the power, yeah, 0.01. So, what is the rate? What is the order with respect to hydrogen? No. Yeah, we got the concentration. So we just take the ratio of this concentration. We got the ratio of the rates. So if you divide 0.1 over 0.001, is it 10? Yeah, so we don't use the pH, we use the concentration because rate is dependent on the concentration, right? Yeah, actually, the rate is second order with respect to hydrogen ions, isn't it? If you see, so you are going to, for a rate, you are going to keep them in as a square. 100. So we are going to get 100. So the value of rate of at pH 1 over rate at pH 2 is going to be 100. And yeah, but it will be a longer way. The smaller way is that we got the concentrations and we know that this concentration with this substance, it's a second order. So we put the concentrations in the formula. And then what we did, we put the squares because it's a second order. Mehaveen, you have to find the change, the factor by which the rate is changing when the pH changes from 2 to 1, right? So we have to identify the concentration. So we got the concentration when the pH is 1, the concentration of hydrogen is ion is 0.1. And when the pH is 2, the hydrogen ions concentration is 0.02, 0.01. So we put these concentration, but we know as it's a second order, so that's why we kept them in a square. And that's how we get by which factor the rate is changing when we change the pH from 2 to 1. The rate is changed by the 100 times. Is this clear now? Okay. Now, B. In aqueous solution, iron 3 ions react with the iodide ion as shown. Okay. The initial rate of a reaction is first order with respect to iron 3 positive and second order with respect to I2 positive, I negative. The mechanism for this reaction has a 3 steps. Okay. So see, from the first statement, can I make the rate equation that rate is equals to rate constant K, concentration of iron 3 positive times square of the concentration of iodine, right? Okay, they have told you that the mechanism for this reaction has a 3 steps. Each step involves only 2 ions reacting together. Okay. Then suggest equations for 3 steps of this mechanism. Identify the rate determining step. Okay. So most important thing is that from this rate equation, we got to know in the rate determining step, there must be the involvement of 1 mole of iron ion and 2 moles of iodide ion because it's a square. Okay. So that is the important thing. That's what you have to do in the rate determining step must have one involvement of a 1 mole of iodine and 2 moles of iodide. Okay. So let's see how we will do it. Okay. So the first thing, and they have told you that in each reaction you can use only two reactants, 2 ions only, not more than 2. So first, if I react Fe3 positive with I negative, what is going to happen? These two have opposite charges. So they are going to attract each other. And as a result, they bond. And when they bond, the net charge becomes 2 positive because 3 plus and minus 1 makes it 2 plus. Is this understandable? Is this point is clear? Now that we got the intermediate in step 1 because we need these two at the end. Okay, but we got an intermediate over here. Now, this intermediate has what charge? Positive charge. So, if you see, there are 2 moles of this and there are 2 moles of this. But by which ion it is going to react? Minus 1. Because it's a positively charged and iron is also a positively charged and the opposite charges always repel each other. So it means in the second step, it is again going to react with the negatively charged ion. Is this understandable? Okay. Now, what is going to happen? There is a one possibility that what is the charge of this? 3 positive. So what happens that if the iodide which is bonded to it loses its electron to iron and as a result iron becomes 2 positive. And now the neutral atom has been released because it's a I negative initially, but that I negative when present over here, it loses its electron to the iron and then as it loses its electron as a So it's a -1 already. So it becomes a 0. Now it has a no net charge. If it's a 0 initially, then after losing it becomes +1. But right now it's a -1 initially. So when it comes out, as it's a neutral, so it can be interacted with either negative and positive. So we got I2, for example, but this iodine has a -1 charge, so that -1 charge stays. So we got our one of the product over here. Now we have to show another product over here, right? And see, we involve both the moles of iodide, but still 1 mole of iron is left, and iron is positively charged and this is negatively charged. So yes, this can be a possibility that the second mole of iron react with this I2 negative, and as a result, this one extra electron is lost by this I2 negative and gained by iron. As a result, iron become iron 3 positive. Yeah, sorry, it gains the electron, so it becomes iron 2 positive, and I2 negative becomes I2. Now, if you see, we got that's the proposed mechanism. The thing is that we have as conditions, we follow only those conditions to make the final product. The first condition was that in each case we are going to react 2 of the ions. And the second condition is that we have to make sure that this can be justified from this mechanism. Okay, is this understandable? Now, if you see, on the basis of this, what can be a rate determining step? Why I is not balanced? Yes, what will be the rate determining step? Yes, very good, Sean. Sean says second one, because if you see how many moles are the order of iodide is 2 and the order of iron is, if you see in the second step, how many iron are there? 1. And how many iodine are there? 2. So it's a second step. Now, you have to think that they are opposite charges, so you are going to react the opposite charges. And you have the focus that you have to make at the end these two, and that can be justified as well. So what I did, I just joined them because they are opposite charges, so they get joined. When they get joined, it's a 3+ and it's a -1, so we got 2+. Now it's a positively ion, so it is going to react with another ion, negatively charged ion. It is not going to react with this. So I will involve this one over here. Okay. But the thing is that I have to keep in mind, I have to make these 2 moles. So, and I have one more step left only. So what I did, I turned this 3 positive into 2 positive over here. And I released the I from here and joined with this. So as a result, it's a negatively charged, so it still stays negative. And as it still stays negative, so it is going to react with another positively charged. So when these two react, this negative ion this electron is lost and gained by iron. So the second iron 2 positive is formed, and we are left with I2. Yes, Sohaib, in the third step, we have a 1 iron. Yeah, but the thing is that this I2 over here made due to this. So indirectly, in third step, there is an involvement of 2 moles of iron as well. If we consider third step as the rate determining step, then the rate equation would be rate is equals to rate constant, concentration of iron 3 positive raised to the power 2 times concentration of iodide raised to the power 2. Why? Because this is formed from the second step, and in the second step, 1 mole is already involved. And here the new iron has been involved. So if we consider third step as the rate determining step, so it means that the rate equation would be like this. Because there are indirectly the first iron is also involved in the third step, because if it is not reacted over here, how could we get this? Is it clear, Sohaib? Okay, Shahan, think, if this ion is not here, then will you able to get this? So it means if this is here, so this ion is also involved, and there is one more ion. So in step 3, actually in equation you are observing only one mole of iron 3 positive ion, but in actual there are two iron 3 positive ions involved in the equation 3. Is it clear now? Okay. So we are done with question number 10. Oh, sorry, question number 3. Now, question number 4. State the hybridization of carbon atoms and carbon hydrogen bond angle in benzene. So I think everybody must remember that it's 120 degree because it's a trigonal planar. C6X6, explain how orbitals overlaps lead to the formation of pi and sigma bonds in benzene, and how many marks it has? 3 marks. Okay. So we are going to cover 3 points. Okay. First, they have asked you hybridization and the bond angle, right? So all carbons are sp2 hybridized because each carbon has a pi bond, right? And bond angle of carbon hydrogen is 120 degrees. Is this clear? Now what they are saying, how orbital overlaps leads to the formation of sigma and pi bond. So how sigma bonds are formed, how the orbitals overlap in sigma bond. No, in sigma bond, how the orbitals overlap. Yes, very good, Shreya. The overlapping is a linear overlapping, head-to-head overlapping. You have studied in AS. And how the pi bonding the orbitals are overlapped? They overlap by sideways overlapping. So you have to write this only. Because see, you have to understand the question what they are saying. Explain how orbitals overlaps leads to the formation of sigma and pi bond in benzene. So don't get confused with benzene. They didn't ask you to explain the whole structure of benzene. They are just asking how the sigma bonds, when the sigma bond is formed, how the orbitals overlap. When the pi bond is formed, how the orbitals are overlapped. Yes. So sigma bonds are formed by linear, or you will write that head-to-head overlapping, while pi bonds are formed by parallel overlapping, or you will write sideways overlapping. Is this understandable to all of you? So it's very important to understand the question, okay? And in this, most of the students do this, that instead of explaining this, they will start explaining that in benzene, there are 6 sigma bonds and there are 3 delocalized. Each carbon has a 1p or anhybrid orbital, and they all have overlapped each other to form a delocalized system. So see, don't get confused with the benzene. Try to read the whole question carefully. Yes. Okay. Now, okay. This is clear to all of you. Okay. Now, compounds that can be synthesized from benzene in 3 steps by the route shown in figure 4.1. Okay. Draw the structures of X and Y. Okay. So if we are getting NH2 over here, it is for sure that the previous one having a nitro group, because NH2 group cannot be directly substituted on a benzene ring. We first got NO2 group substituted over there, and then due to the reduction, and that reduction is done by tin and concentrated hydrochloric acid to turn a nitro group into a amine group. So if nitro group substituted over here, so it clearly indicates that over here we got the alkylation. So if this is the alkyl group, it means the reagent would be like this, having a chlorine over here along with AlCl3 and heat. And over here, concentrated nitric acid and concentrated sulfuric acid and temperature range of 555 degrees Celsius. Yes, is this clear to all of you? Now give the reagents and conditions. So in step 1, the reagent is, this is the reagent. In conditions, we will write AlCl3 or AlBr3. No, you can write in the form of formula as well. CH3 twice CH, and instead of halogen chlorine, you can write Br as well, because both can be used. And in the same way, if you are using Br, so you can write AlBr3, and if you are using chlorine, so you are going to write AlCl3. So this is the condition. In step 2, reagent is concentrated nitric acid and concentration and concentrated sulfuric acid is the condition, and 55 degrees Celsius. Step 3, tin and concentrated hydrochloric acid. Is this clear to all of you? Yes, because see, Shahan, they didn't ask you to write the name or give the structural formula or give the displayed formula. So they just write, give the reagent and condition. So it can be written like this or like this. But if they specify that write the structural formula of the reagents, then you have to write it like this way. And if you write this way, it will be marked wrong. If they have mentioned that write the structural formula. Okay. Now, C part. Compound W is an isomer of Z. Okay. Yes, there are 3 carbons. And then, okay. Give the systematic name of W. Okay. So this is going to be considered as carbon 1. Now you can start number from either side, 2, 3, 4, 5, 6. So the name would be 3, 4, 5. Next, tri methyl. Then benzene ring having an H2 group, what do we call it? Phenylamine. Right? Phenylamine. Is this clear? Yes, because it's a phenylamine. That's what we have studied, right? If this group is there, then we call it phenylamine. So whatever the group are present, we start from here. That is going to be carbon 1. Okay. Complete table 4.1 to show the number of peaks observed in carbon 13 spectrum of W and Z. Okay. And it's a carbon 13. So let's start with Z. In Z, if you see, these two are going to give you a same peak. This one has a different environment, right? And obviously this one has a different environment. And this one too has a different environment because it is bonded to NH2. But this and this one has the same environment because on one of its neighbor there is CNH2. And these two have a same environment. So how many types of peaks we are getting? 1, 2, 3, 4, 5, 6. 6 different types of peaks. Yes, very good, Shahan. So 6 peaks for W. No, it's Z, sorry. Now W. Obviously, this has a different peak. What about these two? Same peak, right? No. This one and this one has a same. Because in these two, this is at a difference of a 2 carbons. But from here, this group is at a difference of 4 carbon. So this one is going to have a different peak. So 1, 2, 3, 4, right? But the other thing, why you are ignoring this one and these two? So again, how many peaks we are getting? 6 peaks we are getting. And the same reason that these two are at a same distance from this. That's why these two have a same environment. And this one has a different environment because this is at a greater difference from this NH2. So 6 peaks over here. Is this clear? Okay. Now, the exhaust system of most modern gasoline-fueled car contains a catalytic converter with the 3 metal catalyst. See, again comes from AS. These metals act as a heterogeneous catalysis. Name 3 metal catalysts used in catalytic converter. Yes, who can recall them? Platinum, very good, Shahar. What else? No, good catalytic converter. Platinum, palladium, rhodium. Okay, platinum, palladium, and rhodium. Platinum, palladium, rhodium. What is meant by the heterogeneous catalyst? So a catalyst which exists in a which is different phase from the reactants. Very good. It is a catalyst which has a different state or different phase as compared to reactants. Okay. The exhaust system of many diesel fueled cars contains an additional system to reduce the vehicle emission. This uses a liquid that is added to exhaust system. The liquid contains urea, which decomposes on heating to isocyanic acid and ammonia. So this is the equation. Isocyanic acid reacts with water vapors to form ammonia and carbon dioxide. Some values for standard enthalpy changes of formation and standard entropies are given in table 5.1. Okay. What is meant by the term entropy of a system? So what is entropy of a system? Measure of a disorder or measure of the randomness of a system, right? It is the measure of disorderness of a system. Now, use the table in table 5.1 to calculate Gibbs free energy for reaction 2 at 25 degrees Celsius. And it's for 4 marks. So that is reaction 2. Okay. Let me write it over here. HNCO plus H2O plus NH3 and plus CO2. To find the Gibbs free energy, we need this expression delta H minus T delta S. right? And they didn't give you either. So you have to calculate the delta H and you have to calculate the delta S and put it in the formula. So they are giving you the formations. If you recall, for the formations, we use the Hess cycle that H2, we could kept the elements over here, right? We need, okay. So over here, water and HNCO is formed. So the formation of HNCO and water are these. So this is going to be X minus 101.7 plus minus 241.8. And the formation of ammonia and carbon dioxide is going to be on either this side minus 45.9 plus minus 393.5. So if you see the Hess cycle, this is the indirect route and this is the direct route. So if I have to calculate the delta H, so delta H is equals to minus 45.9 plus minus makes it minus 393.5, and this minus when it moves to the opposite side, it will become plus. So plus 101.7 and minus plus minus, and when it moves to the opposite side, it also becomes plus. So 241.8. So that's how you will get the delta H. Who is calculating the delta H? Now, the entropy change would be entropy of a reactants minus entropy of a product. That was the formula, if I'm not wrong. No, sorry, it's always product minus reactant. Is what is the delta H value? Sorry? Minus 95.9 kilojoule per mole. Okay, now there is another thing which is student missed. Entropy is always given in joules, not kilojoules. So 192 and 213.8. So 192.8 plus 213.8, these are the entropies of the product minus entropy of the reactant is 238.2 and 188.8. 232.2 and 188.8. Let me check again. 238.2 and 188.8. Okay. Yes. What is the value? And temperature must be converted in Kelvin. So 25 plus 273. It is going to be 298. Yes, what is the answer over here? Minus 20.4. It's in joule. So divided by 1000 to convert it to a kilojoule. So it is 0.1230204, right? Now, Gibbs free energy value will be delta H, which is minus 95.9 minus T, which is 298 times it's minus 0.024, right? So 298 minus 0.0204. So see, that's why it's 4 marks, because examiner want you to calculate each and everything here. Is this understandable to all of you? Yes, it's 89.8, Muhammad Azif. Yes, Vaish, you are getting the same. Yes, minus 89.8 is the answer from Azif. Recheck. You are also getting the same. Okay, that's fine. Okay, so here we are ending today's session. And tomorrow we are going to continue from here onwards. And I'll try to keep one session on Saturday and Sunday as we did it last week as well. Okay. So see you everyone in the next class. Take care and goodbye. Allah Hafiz.